On July 30th, Perseverance successfully launched on its 7-month journey to Mars. At the top of the rover, at the end of a long-necked mast, you can see something that looks a little like a head. It looks a lot like a head, actually, especially because there's a perfect circle on it that could easily pass for an eye. And in a very particular way, it is an eye. After all, it plays a pivotal role in collecting important data from the surface of Mars. This whole unit is a major component of SuperCam. SuperCam is the suite of sensing instruments on Perseverance that will remotely perform analyses of rocks and soils with a camera, 2 lasers, and 4 spectrometers. All of these serve an important purpose, and today we're going to find out what that is and why. I'm Lexi Petronas from the Los Alamos National Laboratory Public Affairs Office. Over the next few weeks, we'll be talking to some of the people on the elite teams behind specialized instruments on the Perseverance rover that will capture images, sound, and brand new data from the red planet. Welcome to Mars Technica. Roger Wiens is the principal investigator of SuperCam. You heard from him in episode 1, and you'll hear from him again. That's because he knows SuperCam inside and out, so he's exactly the right person to explain what SuperCam will do. I wonder if you might give us a tour of SuperCam, if you could just sort of walk us through what it is, where it is on the rover, what it's going to do, just a deluxe tour.
So if you see a picture of the rover, there is a white box that is up on the top of this mast about eye level, and it has one large eye. It's about 4¼ inches in diameter, a kind of a cyclops eye, and that is the SuperCam eye. There is a mirror, in fact a telescope behind that eye that projects the laser light out to the targets up to about 25 feet away. And the laser can be of two different wavelengths. It can either be infrared, which we use like ChemCam for laser-induced breakdown spectroscopy, where we make a little flash of light on the target, a little ball of plasma, and that gives us the elemental composition of the rocks and soils by getting that light back through the telescope into spectrometers. And then there is a green laser beam that we can produce from the same laser, and that green beam will tickle the molecules on the surface, so to speak, and they will produce some light that is telling us the vibrational bands of the molecules on the surface. That gives us some mineralogy and can also look for organic materials. So those are the two sort of main compositional areas, chemistry and mineralogy. One other technique contributes to mineralogy, and that is the infrared and visible reflectance spectroscopy that is done. We call that VIS-IR. And that also tells us about minerals by looking mostly at absorptions in the infrared range between 1.3 and 2.6 microns, so way beyond what our eyes can see in wavelength, but the rocks and soils will have absorptions up in that region that will tell us about the vibrational bonds or the vibrational frequencies of molecular bonds. That is also mineralogy. And then we have a microphone on SuperCam. This microphone can, of course, record sounds of any type that we hear on Mars. Its main purpose scientifically is to listen to the zapping sound that we make with the infrared laser focused down to produce these plasmas. The plasmas they expand supersonically when they are produced, and that makes a little shock wave. And when you have a little shock wave in a plasma, that's almost like a tiny, tiny little lightning, and you get this tiny little zapping sound that is a extremely miniature version of thunder. And so that will tell us something about the hardness of the rocks. Basically, if we do a series of laser pulses into the same spot on a rock, we're ablating a little bit of material, we're making a little hole, and that hole is only a fraction of a millimeter deep usually. But as it goes in, the laser changes its sound with the plasma. And as that changes, we can tell that hole is going either shallow or deep, depending on the amount of change we get. And that's going to tell us about the hardness of the rock. which is really cool because we're never touching this rock. And that's pretty special that we can do it that way. And then we have an imager on board on SuperCam that gives the highest resolution remote images from the rover as well.
Because SuperCam can fire a laser from about 25 feet away to study targets smaller than a pencil point, Perseverance will be able to reach spots that it can't get to with its arm. And while it's listening to the snap of the laser impacts it makes, SuperCam's microphone will also provide first ever recordings of the Martian surface. That will give sound clues about the wind and the environment. SuperCam builds upon some of the technology that's already on Mars in the form of ChemCam. ChemCam is on the Curiosity rover, which landed on the Martian surface in 2012. There's an entire ChemCam team at Los Alamos, which works closely with the SuperCam team and in many cases overlaps. And in fact, there's yet another cam in the works. Why so many cams? They all have unique parts to play. And to wrap your head around what SuperCam will be doing, it's helpful to learn exactly what the other ones do too, from someone else who knows a lot about them.
My name is Patrick Gazda. I'm a planetary scientist on the Mars rover team, and I'm a scientist at Los Alamos National Laboratory.
When Roger was looking for a postdoctoral student in 2014, Patrick was in the right place at the right time. He's been on the Mars team ever since.
I've had a very odd background. I started out as a chemistry undergrad major, and I graduated, I actually studied material science, and then I graduated, and I didn't get into grad school the first time that I tried. So I worked in industry for a while, and then, it's just funny, like, how these things are, that I bought an amateur astronomer, like, telescope, and I was just looking at the night sky, and I was looking at Saturn and Jupiter and the moons and everything, and being like, wow, this is all really cool research. Like, this would all be really cool to research someday. And then I kind of looked into, like, what would it take to study, like, because for a while I was like, oh, the atmosphere of Titan is really cool. What would it take to study this, like, for real, like, as a scientist? And so I learned about these astrochemistry groups, and I learned about astrobiology, and I was learning about these other things. And I'm like, wow, maybe I should go back to grad school.
And so I just read some news about the Organicam, which you're also working on. And it struck me that there are a lot of cams. And I wondered if you could sort of just lay out for us the different, just like a primer on the different cams. And
so ChemCam, that's the famous operating instrument on Mars, and then all the other cams sort of flow down from that. So of course you have SuperCam, which is on the next rover. That's the LIBS, which is just like ChemCam, but also Raman spectroscopy, and then it can also do infrared passive spectroscopy. In grad school, I did both LIBS and Raman a whole lot, so I do know quite a lot about those two techniques. And then there's the last technique that SuperCam can do is called time-resolved luminescence spectroscopy, which in a way wasn't really designed to do, but it's a capability that it has. So it's designed to do time-resolved Raman. The reason why it does this is because when you excite a rock with a laser, it will start emitting all sorts of light at different times. So you can have really fast, emission, which is Raman, and then you can have really fast, if there's organics in the rock, they can also what we call fluoresce, so they glow for a long period of time. But minerals also fluoresce, sometimes very strongly. And so to pick apart those signals, if you just take your video camera and just turn it on, you'll see all these things glowing at the same time, which isn't really helpful, right? So what you want to do is you want to have a camera that can record in like 100 nanosecond increments, which is what SuperCam can do. So you can take a picture of just the organic fluorescence, or you can take a picture of just the mineral, what we call luminescence. So that's for SuperCam, it can do that on a point per point basis, right? So it has that telescope just like ChemCam does. It shoots a laser at a point and then collects spectra from that point. Now, Organicam kind of takes that part to the next level, where instead of shooting a point laser at a place, it illuminates a huge area in front of your rover or whatever with a laser. And then instead of taking just a point spectrum, it takes an image of that whole illuminated spot. And since you have a camera instead of just a telescope, you can actually get an image of where all the organics are in that illuminated area. I don't know if that makes sense without a picture.
A complex instrument like SuperCam requires a lot of hands. In fact, there's a long list of people who can say that their hard work has touched another planet.
Here in Los Alamos, we had probably on the order of 150 people working on SuperCam in some way or another. I know that because we had invitations for a special event that went out to that many people. But of course, a lot of it was done by a much smaller core team. Here in Los Alamos, we built the body unit, which is really the control center of the instrument, and the 3 of the spectrometers that collect and record the light, some of them quite specialized for this. There is also the other part of the instrument, which is called the mast unit, is the part that sits up on top of the rover. And that part was actually built in France. And it's a contribution by the French Space Agency, so the American taxpayer doesn't pay any for that. And there was a similar group of maybe 150 people in France that worked on it. And so we had that group as well. And then there was a group of people in Spain that were building a calibration target that went on the back of the rover. And in fact, there were even people in Canada and Denmark that contributed to that part. So it's a really international effort, spearheaded mostly here in Los Alamos and in Toulouse, France. And then, of course, we also had some people at Jet Propulsion Laboratory in Pasadena who were helping us by way of trying to make sure that this instrument would be well accommodated onto the rover.
The rover is already on its way to Mars, but we still have a lot to talk about. Coming up in the podcast, we'll talk about the unique battery source that powers Perseverance, what exactly it means to look for signatures of life, learn how it's possible to steer a rover on Mars when you're living on Earth, and a lot more. Mars Technica is produced by Los Alamos National Laboratory. Joey Montoya is producer and editor. Lexi Petronis, writer and host, with special contributor Laura Mullane, and additional thanks to Scott Falk, Charles Poling, Camille Dixon, and Arthur Bishop. Find out more about the laboratory and its mission at www.lanel.gov.